Next speaker is Professor Parthasarathy Majumdar, who is a senior professor at the Saha Institute of Nuclear Physics in Kolkata. His broad research interests are black holes, loop quantum gravity, and gauge field theories. He is well known for his work on black hole entropy. I might add that he had the early part of his career here, right here, and therefore is very well known to all of us, and welcome back to this place. Partha will speak on the Chandrasekhar mass limit and quantum gravity.
Thank you very much, Professor Balakrishnan. It's really an honor to be a part of this Chandrasekhar centennial. I should begin by begging your indulgence on daring to speak on the great work. I would say that this is a product of my fascination with it. I really am not an astrophysicist and have not sort of extended it in any way. But reading Chandra's Nobel lecture, I was amazed by the structure of just the formula. And because I have been dabbling in quantum gravity for a few years, I thought maybe it's worthwhile to find a connection. Unfortunately, that didn't happen for a long time because it's so bizarre to think of such a thing. And it's only a few days ago, in fact, Ghanshyam, one of the organizers, and I were corresponding by email, and then I changed the title of my talk. I was thinking of talking on some more formal work, but I just couldn't resist the temptation of coming to this centennial meeting and discussing the work of the great master. So with those apologies, let me begin. This is, of course, the formula that everyone knows, the formula that Chandra wrote down at the age of 20. The mass bound, stars heavier than this bound, evade the stage of the white dwarf. And some of them, of this core which is left over, there's a further gravitational instability. If this mass is bigger than, let's say, 2 solar masses or more, as we heard from Professor Ramesh Narayan the other day, this will collapse to a black hole. So what's so great about this? I mean, this is all very known, very well known, and people are working on it. Of course, gravitational collapse continues to be a very difficult topic, very complex phenomenon. And I do not think anyone here would claim that he or she has a complete understanding of all the stages of this phenomenon. So I went back to reading, and this is of course a very beautiful phenomenon, and therefore one has to go back to read the master again, and none better than this Nobel lecture. And this is the formula which sort of intrigued me. So writing the formula down in terms of the solar mass, is probably not so deep, because you could have written it down in terms of the mass of another star. But Chandra, in his Nobel lecture, chooses to write it in terms of fundamental constants. And this was amazing for me because of the appearance of this fellow here. I'll elaborate as I go along. But the first thing I should do is to give you a glimpse of how this comes about, especially because some of our younger friends in the audience may not remember this. So this comes about, this formula, this lower bound on the core mass for this star to collapse to a black hole comes about because of a hydrostatic equilibrium between the pressure, the inward attractive forces due to gravity, and the resistive forces coming from the Fermi degeneracy of a relativistic degenerate gas of neutrons. So one way to do it, and this is of course not the way Chandra does it in this paper, but this is something that more modern treatments do, is to begin with the Einstein equation, because if you have a degenerate gas of neutrons compactified to a volume which is of a sphere of radius a few kilometers, then obviously general relativistic effects would be large. So it's safest to begin with the Einstein equation. Maybe with a spherically symmetric ansatz for the metric, and imagine that you have perfect fluid. So perfect barotropic fluid, pressure is a function of the density alone, and then the equation you get is a very famous Tolman-Oppenheimer-Volkov equation. that equation tells you what the core pressure is. So this is the equation that you have to solve. And if you imagine, so this is the thing P, rho, and M here are functions of the radial coordinate r, like so. And I'm putting these constants equal to 1 just for the time being. I'll put them back momentarily. Now if we assume that the density is uniform, so that the mass at any radius r is given by this formula, then in fact you get a solution. And here I have put back the constants G and C. So the core is, the pressure at the core is simply given by this formula here, where Rs is the Schwarzschild radius given by the standard formula. Okay? So that gives you the pressure of gravity. That's pushing down on the neutrons and making them collapse. What's resisting that is this. So I've simply taken over, excuse me, my throat is a problem, sorry. So I've taken over the formula that, you know, every one of you know, whoever has dealt with degenerate electron gas, standard quantum mechanical exposition, you know that the degeneracy pressure is given by this, where n total of P, n total of Pf, where Pf is the Fermi momentum, is given by this formula. And indeed, the additional input which Chandra gave to this was to generalize to a situation which is the correct physical one, namely where the particles, the neutrons, are relativistic, and of course this should be really nearly equal to. But this less than simply means that the degeneracy pressure is bounded from above by this, and if you now use the equilibrium, this is probably hard to see, I don't know, can you see this? Wrong choice of colors. Anyway, so if you equate these two, the core gravitational pressure with the neutron degeneracy pressure, out comes the formula which I had written down. So I've convinced you, a la Chandrasekhar, that this formula comes from pretty well-known theories of physics, general relativity on the one hand, and a special relativistic equation of state for the neutron gas on the other hand. So there's nothing exotic about this, except when you re-express this like this. So when you re-express this like this, suddenly you realize that we are dealing with Planck scale. And not only are we dealing with Planck scale, we are dealing with it in a non-perturbative way. So the Chandra limit, in which physics at the Planck scale played no visible role, somehow the physics has conspired to produce something where the Planck scale appears non-perturbatively. By that I mean, you can of course write this as a mass and convert that into a length as well, the MP, as I think in one of the talks somebody showed you how to do it. I think it was Sam's talk yesterday, showed you how to derive the Planck length and the Planck mass. So if you did that calculation, then of course you see that as in the limit where Planck length goes to 0, that's the limit we say that we want to, that's a sort of the limit where quantum gravity effects should be small. You find here on the other hand that this effect is very, very large. It's certainly increasing as Planck scale goes to 0. So that for me was rather weird, and that's mainly because we are taught, everybody here knows that we are taught quantum gravity effects must be very, very small. They must be of order Planck length, and here we are, somehow this formula does not seem to behave that way. So now this reminds me of something I've been dealing with. Here was where we started doing this, I think about a decade ago, black hole entropy. This has the same property. Now I would like to just mention, in view of Padmanabhan's talk, that my view of black hole entropy is different from what is commonly called walled entropy. The walled entropy is not quite an entropy. An entropy involves something that you can count, a la Boltzmann. Walled entropy, there's nothing to count. It's an entropy function. So the way I think of walled entropy is exactly what Padmanabhan said, namely, it is a function of the geometry, of the metric and so on, in such a way that if you confined yourself to GR, to general relativity, then that function would simply be the area. There's no entropy associated with it. Space-time does not have an entropy. Classical space-time cannot have an entropy. So it's just the contrary view of what you heard before. Entropy arises as a consequence of quantization. So Boltzmann is, of course, the forerunner of quantum mechanics, even though he couldn't have derived Schrödinger equation like Paddy said. But without Boltzmann, we probably wouldn't have thought of quantum mechanics. So it's that I'm trying to get at. So black hole entropy for me is a consequence of the fact that you have in your mind a picture of a quantum space-time. Okay? So in that sense, this is where, so I would like to distinguish LP squared from G. LP squared, as I have written down earlier, is G h bar over C cubed. So it's really the h bar there which brings in the quantum, G, h bar, and C. So this is the other thing which inspired me. And so I asked these two questions. And of course, I do not have by any means complete answers. Is the mass bound linked to quantum gravity? That's the title of my talk. And of course, the derivation that I did, the sketch, does not give us any inkling of that. It uses GR in special relativistic quantum mechanics. Further, are the mass bound and SBH related, the entropy? This looks even more bizarre. But let me just go on, and maybe all my ideas will die by the end of another, what, half an hour, or maybe 40 minutes. But even so, I think I would have made you think. The question that I want to begin with is ask, did the derivation I gave you use a consistent formalism? And I would like to say no. Why is that? Well, when we teach, and some of you I'm sure have had courses on quantum field theory, we begin by saying a relativistic quantum mechanics is not a good theory because of the possibility of particle production. So you can't have a theory which describes one relativistic particle. It will, if it has enough energy, pair production will happen, and soon you'll have an infinite number of particles to deal with, for which you must go to a field theory, special relativistic quantum field theory. But on the other hand, the way I computed the gravitational pressure was using GR. So if you really want to be consistent, you should not be using special relativistic quantum field theory. You should be using general relativistic quantum field theory. Now you could say, oh my God, this guy is crazy. This is going to be horrendous calculation here. I agree, and I have not even touched it. So, you know, if you feel that way, I completely agree with you. But I want to go a bit further. I want to say that even quantum gravity effects may not be small for some of the reasons I sort of was trying to hint at. Again, as I said, I don't have, you know, unlike the previous talk, I have the germination hasn't quite happened. It's happening, and maybe the fledgling will die. But I just need to argue that quantum gravity effects may already be there. Why am I saying that? Before I come to that, I'd like to say that my view of the Chandra limit is that of getting the right answer using quote-unquote an invalid theory. What do I mean by that? Well, I'll give you examples. Mitchell's 1784 derivation of the Schwarzschild radius. We heard this about this earlier from Abhay Ashtekar, and he got the coefficient 2 right. So was he discussing the right physics? And Abhay told us that he wasn't. Okay. Similarly, Niels Bohr was using classical mechanics with some ad hoc assumptions to derive what we now do routinely in quantum mechanics, the Bohr radius. So are these any good then? I mean, you get the answers which you later on derive through what is the right theory, and I would say that they do. They are sort of pointers to the right theory. General relativity in the first case and quantum mechanics in the next. So the question that one would like to ask in the same vein is, what theory does Chandrasekhar's bound point towards? Okay. Now, I want to re-express the bound in a more suggestive way. And you see, the way I have done it, it's now a ratio of areas. Okay, lambda Cn is nothing but the Compton wavelength of the neutron. So since this is square, this is the Compton area of the neutron. And this here is then a ratio of areas, Compton area of the neutron normalized to the Planck area. And the condition, the mass bound can be interpreted, I mean this is again the standard interpretation, that is a condition for instability with respect to the formation of a horizon. Now horizon here I would say is a null hypersurface with special foliations being trapped to surface. The trapping is important. I mean it's slightly different again from Padmanabhan's, I mean he was sort of thinking of a holographic surface as a horizon as well as an ordinary null surface without this aspect of trapping, but I shall not get into that. So I would suggest that the existence of this bound, the condition of instability of a very massive core of a star, is actually the condition for stability of horizon with respect to Hawking radiation. Now this is something that I have been working with for some time. What is this condition? So if you associate a mass with a horizon which has an area, then the bound that I was able to derive, and I shall sketch this for you, in fact that will be the most of the talk, is something like this, where SA horizon is the microcanonical entropy. So this horizon here is now what one may call an equilibrium or an isolated horizon. It's not a dynamical horizon. So we are talking about something, a null surface with trapping properties and so on the foliations, after things have settled down, okay? And then I can say that this will happen, that there's a bound, a lower bound on the mass of the horizon. So the question is, how does this bound come about? I will give you heuristic arguments for that. And then of course the harder question on what is the link between these, I shall only touch upon because as I said, the idea is still in the germinal stage. I don't think I can really go beyond that. But I promise to work on that and come back and tell you a more solid thing in the future. So let me take a digression now and try to motivate this bound for you. Where does this bound come about? So in any quantum general relativity theory, so now we are thinking of quantum general relativity, quantum space-time. So think of quantum space-times. Think of quantum space-times where there could be a horizon or a boundary. And the Hamiltonian operator, I'm asserting that this would be sort of a sum. Of course, this is very heuristically defined, would be more rigorous in this definition, but let me write this anyway. And the states of this space-time are now written down in terms of the bulk and the boundary states. Now you might think, aren't the boundary states determined by the bulk? Well, the idea here is that the boundary states classically are, of course, classically the boundary geometry is determined by the bulk geometry. But when you quantize the system, the boundary states have a life of their own. The fluctuations there are not tied to the fluctuations in the bulk. So that is why it's perhaps okay to write this. I should say that this is not something that I've written down first. Other people have done it, and this is some common practice. Now, one thing about relativity, GR, is that there is no notion of gravitational energy in the bulk. I think it was just mentioned in one of the discussions that gravitational energy really lives on a boundary. So it is, and this is in the classical theory, this is articulated by saying that the bulk Hamiltonian vanishes. So I'm using that here, and when I use that, and I work out the partition function, the canonical partition function, so I have these states with, so this is very, very ad hoc, very heuristic. I have this set of quantum states interacting with some sort of a heat bath. Now, if you want to be more specific, you could think of black holes, and the heat bath is nothing but the Hawking radiation heat bath. So it's possible to realize this physically. And then one shows that the partition function is simply the boundary partition function. The bulk states have decoupled, and this is what I call thermal holography. Now I should mention that holography comes in various sizes and shapes, and Professor Padmanabhan described one version of it. There is also this version, related version, which is called the holographic hypothesis, Now here, of course, I am not making any hypothesis except the starting point, which I don't think is really a hypothesis, but this is a straightforward one-line calculation. So I have a derivation of a version of holography, which I would say is a weaker version of the holographic hypothesis, which says that all the states of the system are on the bulk, are on the boundary. I'm not saying that. I'm saying that the bulk states do not play a role in thermodynamics. In space-time thermodynamics. I'm not talking of ordinary thermodynamics. Okay, so as I said, I'm thinking of a canonical ensemble of isolated horizons, and they're characterized by something again which Padmanabhan mentioned, namely the area is actually quantized. And here I look at a very simple situation where the area is quantized equispaced in an equispaced manner. So you have to think of, just like you have harmonic oscillator states, you have area states with area gaps and so on. So you have equispaced area eigenvalues here. And therefore, so you have this boundary. Now I'm specializing to a situation where I'm looking at the boundary corresponding to some sort of horizons here, isolated horizons. You also have the boundary at infinity, and those considerations should be included if you want to do a proper job. I'm not doing that, because I really want to just focus or sort of sketch a derivation rather than go into full technical details. So what you get here, sorry, what happened? Yeah. So using this, you compute the partition function and you do some sort of a saddle point approximation and so on. But the answer that you get is just this. So this is the equilibrium horizon. The answer comes out in terms of S, which is the microcanonical entropy of this equilibrium isolated horizon, minus beta times the mass. And there's this correction factor which comes from the fluctuations. So what I'm doing is I'm keeping fluctuations around the horizon. And when I do that, I can compute the canonical entropy using the standard thermodynamic formula. So the canonical entropy is indeed equal to the microcanonical entropy, but for this extra additional factor which comes from the thermal fluctuations, log delta. And if I really want to give this quantity a status of entropy, of course I'd expect this to be positive real. I will show you that it is later on. But I would also expect this to be positive real. And that's what I mean by an equilibrium ensemble. So if there is equilibrium, then this delta better be real for the canonical entropy to make the sense that we ascribe it in thermodynamics. And this is the condition that we get. When you look at this, this comes out immediately. Okay? So the stability, so this is what I call the stability. Now why do I even discuss stability? Is there any reason for a black hole horizon to be unstable? Indeed it is. In fact, most black hole horizons are unstable under Hawking radiation, which is why you hear about evaporation. But there are situations where the black hole horizon is stable in semi-classical systems. But what I would like to draw your attention to is that I have not actually looked at specific black holes. I've taken a rather very simple-minded model, used some quantum arguments, like the area being quantized, and I've come to a bound on the mass of the horizon in terms of its microcanonical entropy, which I haven't told you what it is, I'll tell you just now. And then this is what I have. Okay, so the question is now, what is this fellow? S horizon. So the idea of isolated horizon you already heard from Professor Ashtekar, was of course theirs, started in 1997, and they have extensively worked on it. Then there was this issue of what are the degrees of freedom and what are the dynamics on such. And then once you know the degrees of freedom, the dynamics, the states on the horizon, you count the states, and that you should get the entropy from state accounting. I'm sorry for the choice of colors. I mean, this is something, it always happens. The projection colors and the colors you see on your screen, I'm seeing it perfectly on this screen, but I'm sorry if you can't see this, but let me just explain this. So here is a collapsing body, and here is what we would say the formation of some horizon. It's really the apparent horizon or or an isolated horizon. This is really the formation of an isolated horizon. But then something happens. There's a shell of matter that comes in, and so the isolated horizon H changes to another isolated horizon H prime. Now, these are not event horizons, because I'm only taking a local view of them. These are described locally completely. An event horizon requires that you know the entire future, teleological, but I don't need to do that. And this is the other sort of Penrose diagram to explain that. So there is my horizon H, and then stuff falls in. So this part of the horizon, I would say, is some sort of a dynamical thing. There's a change, and this changes when things settle down to another horizon H prime. So as you see, I have shown here, I mean, it is not to say that there couldn't be any stuff here. Unlike event horizons, there could be lots of stuff here, but nothing should cross the horizon. That is the isolation, which means that the area of the horizon stays fixed, at least from this time slice to this time slice. So now we would like to ask the question about what are the degrees of freedom and what is the dynamics. There are many ways to do this, many formal, beautiful, nice, mathematically rigorous ways, but I'll just describe something that we did very recently, and this is perhaps the quickest way of doing this. You start off with the Schwarzschild metric, choose a set of tetrads, and compute the spin connection coefficients and the curvature components. This is very standard GR stuff, textbook. Now this is not so standard. You have to define out of these guys something called the Barbero-Yimitsky SU2 connection. I'm not going to do that, not get into technical details. And once you do that, from the bulk you pull it back to a horizon, to the Schwarzschild horizon. So I'm doing this completely in the context of the Schwarzschild solution. And you compute the curvature on the sphere, okay? And you also look at the cross product of the tetrads in the bulk and pull them back to the horizon. So this is spherical foliation. So these are like time slices of the horizon. The horizon has the topology S2 cross R. So if R you take as the time direction of time, then the foliations are simply S2. What is the result? Well, this is the result. This is the cross product of the tetrads pulled back to the horizon, and this is the SU2 gauge field strength or curvature. And the K, the coupling constant here, is a number times the area of the horizon. So this is a derivation. This is not a very difficult derivation, but if you really want to know the details, it's available in our paper. What is this equation of motion? Well, this is nothing but the equation of motion of a Chern-Simons gauge theory. That's what it is. So what we're saying is, if you begin with the Schwarzschild solution and you follow the procedure I did to find out what the degrees of freedom on the horizon are, they are nothing but the SU2 Barbero-Yimitsky gauge connection pulled back to the horizon. And what is the dynamics? This is nothing but the Chern-Simons equation of motion. Now you might say, what is this Chern-Simons equation of motion? Why not something more familiar like Yang-Mills? You see, with a null surface you couldn't have had Yang-Mills for the simple reason that the metric, the 3 metric on the null surface is degenerate. So you have to have a theory where you don't, on the surface, where you did not have to invert the 3 metric. So the theory had to be topological from that point of view. And if you think about it a little bit more, you will sense that in the formalism that we are discussing, the Chern-Simons is unique, okay? Now you can further go ahead, as many people do, and we have shown this, that you can actually gauge fix this SU2 Chern-Simons to a U1 Chern-Simons, but that will also include extra conditions on these sources. So when you pull them back, for instance, if you take a particular direction in the internal SU2 space and project that, and you say that, okay, that's really my physical direction, you could do that, but there'll be extra conditions. So eventually, you'll have to deal with SU2 dynamics, SU2 Chern-Simons dynamics. Now, this is something which has been going around a lot, especially in the string theory literature, gravity gauge theory link. Now, it is all based on some conjectural ideas. Here, this is a derivation. It is not due to us alone. We have just done it in one particular way. It was actually initially initiated by Abhay Ashtekar's group, and many people have worked on it. But what I'd like to say is that as opposed to the string theory way of doing it, here this is a derivation. This is exactly a gravity gauge theory link, except that it's a link to a topological theory rather than a conformal theory. Okay, so loop quantum gravity. What is loop quantum gravity? I can't really get into that, but what I'd like to say is simply this, that loop quantum gravity gives you a picture of quantum space. Quantum space is this set of noodles, Maggie, where the holes are roughly the size of Planck area. Okay, so that's the way you have to think about it. I was explaining to some of the kids that my way of saying this is my kurta here. At long distances, it looks like a perfect continuum. Otherwise, I wouldn't wear it, right, if it were not. Whereas at short distances, you can see the holes in it. So if you go to Planck scale, these holes would become apparent to you. If you build a Planck scale accelerator, you would see this granular structure with holes. So loop quantum gravity gives you a particular kind of granular structure known as a spin network. Now, this, I would say, is an effective quantum horizon. Why effective? Because, you see, in my understanding, general relativity is very vast and includes solutions with or without horizons. Now, of course, you could have null surfaces there and you could attribute them some properties, insert them in a space-time, but the kind of horizons I'm talking about are those which are born out of the field equation. So they're dynamical null surfaces. I'll show you a picture a little bit later. So we do not have such a dynamical thing here. In other words, we have not solved the quantum Einstein's equation, which I wrote down a few minutes ago, and we have not shown that such a surface actually emerges in some limit. I haven't done that. So what we are doing instead is taking this space with the noodles and putting a sphere, and then saying that, well, I know that Chern-Simons fields live on this sphere, and they interact with these as point sources. So these are the noodles. Noodles, each of these carry spin. Now you can't probably see this, but I have different colors for the different noodles. And these colors are supposed to represent spin, 0, half, 1, 3/2, anything. So the punctures carry spin, and this is the formula that one gets if you then count the number of states corresponding to this system. Just a word about it is that, of course, you see the area law right here, but you also see these corrections, and Professor Balakrishnan mentioned this was done here. These whole set of corrections, of course, we really found this and the next term, but this is an infinite series, were found here in this institute when I was still a member of this institute. And I would say that these are the signature loop quantum gravity effects. You see, you can produce the area law in a million ways. So if you say that, oh, I have a new theory of quantum gravity and I found the area law, no big deal, because somebody else will find the area law some other way. So you have to say what your corrections are. Indeed, that's precisely what quantum mechanics did as opposed to the Bohr model. The quantum mechanics did not reproduce the Bohr model, but went beyond, give you a whole slew of corrections. And these corrections became measurable. Unfortunately, I cannot measure these. You can see they're exponentially small compared to the area law. So even if you could measure the entropy, you need far more sophisticated instrumentation to measure these, but still, in principle, they're there. And as a corollary, this was also mentioned by Paddy. He actually wrote down an expression for the Hawking temperature, but since he did not do quantum gravity by his own admission, I can say that if you take this correction seriously, you can show that the Hawking temperature also has a slew of corrections, but of course they're sort of damped because the initial correction is already damped by area. Okay, so some of you might already be bored with all this Chern-Simons talk, so I have a sort of a quick and dirty way of getting it. Not really mine, Wheeler and 't Hooft championed this. Take a fishnet and wound a sphere by this fishnet. The fishnet, the holes have Planck area. So obviously if you count the number of such plaquettes in this lattice, it will be the total area of this sphere divided by the Planck area. That's the number of plaquettes you have, little holes. And now place a spin half in each of these holes. That's very good. So actually you could replace it by any binary variable, but let's think of spin for definiteness. However, because we are dealing with a theory of gravity, which you know has a gauge invariance known as local Lorentz invariance, and this is something also which was mentioned, you have local frames, so you can actually behave as if at every point you have a special relativity. Now we can't deal with the full special relativity, so what we deal with is the rotational part of it. So then we require that we only will count the states which have a total spin 0. And that's the answer. Just a combinatoric problem. This is the part which gives you m total equal to 0. You know, the azimuthal quantum number equal to 0, but this is the part which you must subtract off so that you can get j total equal to 0. Very, very simple. And when you write these combinatoric factors out in terms of factorials and go to the Stirling approximation and use the fact that P is related to the area by LP squared, then you get the same formula which I had written down earlier. Okay. So now I have, I think, 10 more minutes or something, maybe 7 more minutes, and in that I'll try to give you the relationship. So I'm back to my collapse problem. This was just a long interlude because this I could hide behind old work to, to escape from the paucity of new. So basically, let us assume that there's not much energy loss happening, so that the mass of the black hole, or mass of the collapsing body, totally enters the horizon. This is a picture of that. So these yellow guys are the collapsing, are time, so time flows this way. These yellow guys are different representations of the collapsing body at different times. You can see they are shrinking, shrinking, and shrinking. But inside them, a horizon is being born. So these are dynamical objects. These are horizons in some dynamical sense. I would attribute to them the same trapping properties that I attribute to real horizons. So there they are, here, here, and so on. And they coincide. These are, of course, increasing in area. The big ones, the yellow ones, are decreasing, as they should, because they represent shrinking spheres. And they coincide. When they coincide is what we call the birth of the horizon, because then the horizons become accessible to asymptotic observers. So that's the birth of the horizon. Of course, this yellow continuous line represents the envelope of the body which is collapsing. It goes on to collapse to a singularity. That's the line of singularity. So if we agree with this, then I would say that energy loss being small simply translates to the condition that the mass of the core is bigger than the mass of the horizon. So immediately, because it's going in the right direction, I could write this down from my law, from the formula I had for thermodynamic stability. So this is exactly what I said. Each of these guys, mass flows in, can't get out, and the area keeps increasing till this is here. And at this point, you can see the entire collapsing star has gone inside. So this part, everything is happening only inside the horizon. Okay? And this is the other view using a more sophisticated representation, the Penrose diagram. So this is the collapsing body right here. This is past null infinity, future null infinity, and this is time like spatial infinity. And here we are, these are our time slices, different times looking at this. So this is the time at which the horizon is born, but then I would say that this hidden horizon is born way back here, and it continues to grow, and then suddenly it comes out into the open. Okay? So this is what I said, core collapse pushes energy into the hidden horizon, and the hidden horizon area continues to increase. And this increase stops when the entire body has actually gone into the horizon, and it's no longer hidden. That's what we call our horizon. I know Pankaj will not be happy with this picture. This is not the picture that you are happy? Okay. Okay, so now this is the, the weakest part. Yeah, I mean, I'll have nothing to say about naked singularities. It's really outside this horizon business. So this is the weakest part. I don't know why this should be so, but I would imagine that I would like to associate the ACN, the Compton area that comes in the Chandrasekhar formula, with one of these hidden horizons. And you can kill me for this, but this is it. So my idea of the Chandrasekhar mass limit is that somehow it knows that there is a bound from quantum gravity, and it is in fact the same bound. Okay? So the only virtue of what I have said before is that I have actually not anywhere used any classical metric. So I'd like to emphasize that because it's supposed to be quantum. So it's really independent of classical metrics. It's treated as a quantum hypersurface, the horizon. Degrees of freedom or Wilson line excitations of Chern-Simons, which is a quantum topological gauge theory coupled to point sources. This is something I already said. The question now, of course, is does such a hypersurface actually form? Does this hidden horizon, does this really exist? It's very hard to answer this question in a realistic model of collapse. The best I can do is look at simple models. So this is what is ongoing. I have maybe wrongly persuaded one of my students to look at the Oppenheimer-Snyder model of pressureless dust collapse and to actually see how these horizons form, maybe make a movie out of it. Okay, maybe I can show that in some next thing. Okay, so what are the pending issues? I'm basically done. I need to establish a firm relation between ACN, the Compton area, and the hidden horizon. I haven't done that. The full scenario I need to justify in detail, at least by some analytic calculations in simple models. So the Vaidya metric would be another model which I would like to try out. And I would have to go beyond. Okay, so this is a problem which is highly non-trivial. I would like to go beyond this idea of the effective quantum horizon. And the way to do that would be to solve the quantum dynamics problem in loop quantum gravity. I don't know if this is a feasible thing to do, not at this present level of technology. But I would say that maybe with some effort, with some imagination, one can get there. But certainly, a horizon as a dynamical surface is something that we must be able to find out. Okay? I mean, the Oppenheimer-Snyder will only tell me classically what's going on, and then I can wave my arms and again talk about effective quantum horizons and so on. But I think this is really the thing that I'd like to talk about. Okay, I guess that's it. Thank you very much.
Thank you.
Yes.
Yeah, I just have a minor technical comment on
Yeah.
this. What you said about the Wald entropy. I didn't get a time to say that in my talk, so let me just make a comment about that. In the original derivation of Wald entropy, he writes down quite correctly an entropy function, and then says that when you evaluate it on an on-shell horizon, it will satisfy the requirements which we expect it to satisfy for an asymptotically flat space-time and Lovelock theory and all that. It turns out that there is a completely alternate way of looking at the whole thing. That if you know the number of degrees of freedom per unit area in an arbitrary theory, then somewhat like this Plaquet argument, you can actually calculate the entropy.
Oh, yes, yes.
Now, given the field equations, once I use the equipartition, I can actually get delta n for the Lovelock. Therefore, I can count the entropy. But what I did not emphasize is that there is a completely independent derivation of the entropy, and it turns out that it is equal to the Wald's entropy. So it looks like Bob Wald had quite a vision as to what the right thing should be in some sense. And this is completely local, and it is exactly what you would expect. So in that sense, I think hereafter we can call PABCD as the entropy tensor and the Wald entropy as the counting entropy, not just as an entropy function.
Yeah. No, my only point was that, well, I was referring to the original Wald and Iron-Wald work. if you take this it for bit kind of picture, certainly you have already started counting, and all bets are off from my side. But I think it's also good to mention that, you know, this it from bit doesn't tell you what the sphere is.
Yeah, but more than that,
right? I mean, you can take a.
counting is usually done for area.
Yeah.
Now I can generalize it for an arbitrary level.
Mm-hmm. Okay. Yeah.
I am from a very different background. See, you said you are connecting two bones as found by Chandrasekhar and from quantum gravity.